Equation of a plane in parametric form?
This isn't even my final form.
Of course, we also have the normal form. And you, the Cartesian form. First of all, what is a plane again? We already know that from the last video. It's an infinite flat sheet that somehow exists in space. One way to describe it is in parametric form. First of all, you need a support vector, which brings you to the plane, and from there, you go off in two directions. These are given by two basic vectors. It's important to remember that they cannot be multiples of each other. So now we need a scalar or dot product. For that, we have to know we multiply the two vectors component by component and add the products, and this gives us a number. If this number is 0, then the vectors are perpendicular to one another. But one thing you still need to know for this video is the cross product of two vectors which aren't multiples of one another. Basically, this calculates a vector which is perpendicular to the two original vectors. To get that, you write each vector twice, one under another, and then add the crosses like this. You multiply along those crosses and write the answers, with their correct signs of course, as a vector. Don't forget that these three values in the purple lines have a negative sign. In this video, we'll call the vector n for normal, because the normal is perpendicular to the other two. Huh? Normal? Has that got anything to do with the normal form for the equation of a plane? Exactly. You can also construct a plane with only two vectors. Let's see what Giesecke is up to. Today, he's on his way to Mars. He's sitting in his spaceship and looking out the window. The floor of the rocket, which Giesecke is standing on, is now a plane that we can play with. It doesn't matter that it looks so steep, because Giesecke is up in space and won't notice it at all. But if we want to know which way Giesecke is going in space, we need a coordinate system. So let's just take the Earth as our origin. The equation of Giesecke's plane is 2, 8, 2 plus s times 5, 0, minus 1, plus t times minus 3, 1, 0. The support vector points from the Earth to Giesecke's feet in the spaceship. Giesecke always stands perpendicular to the floor, so Giesecke points in the same direction as the plane's normal vector. Now if we fire up the rocket, we can clearly see that the vector is perpendicular to the plane. If we want to define this plane, all we need to know is at which point and how Giesecke is standing. Then we can determine the direction that the plane is tilted in. So if Giesecke flew into some turbulence, and we saw him standing like this, then the plane would be tilted like this. So once again, we only have to know where and how Giesecke is standing. Or, to put it mathematically, to describe the plane, we need its support vector and its normal vector. If we have the support vector and the normal vector, we can write the equation of the plane in normal form. So we have the support vector, that's this guy here, but we still need the normal vector. How do we calculate this one? Well, we know that it has to be perpendicular to the plane. We have two basic vectors which lie on the plane. Therefore, it must be perpendicular to both of those. To calculate the vector that is perpendicular to two others, we know how to do that, don't we? Right, the cross product. So the normal vector is the cross product of the two basis vectors, and that's what we're going to calculate now. First, write the vectors one under the other. Then, draw the crosses. Multiply along those. Put everything together, and we're done. Try that yourself and see if you get the same answer. The vector comes out here and stands perpendicular to the plane, so it points from Giesecke's feet to his head. Well, how do we use this to describe all points on that plane? Let's take a look at a point outside the rocket. It has the coordinates 1, 10, 1. Does that point lie on this plane? Well, let's see now. Better in 2D. Here we have our plane in yellow and Giesecke who is standing on it. Our point x, 1, 10, 1 lies somewhere here. Now let's replace Giesecke with the normal vector. We're interested in the vector connecting Giesecke with the point. That's this vector here. Subtract one vector from the other, and done. And you see, if these two vectors are perpendicular to each other, then the point lies on the plane. If they weren't perpendicular to one another, say with an angle of 60 degrees between them, then the point would be outside the plane. To check whether the normal vector and px are perpendicular to one another, we can take the scalar product and see if it is exactly 0. If that applies, they are perpendicular to one another. So let's run through the calculation and out it comes. 0. The connecting vector is perpendicular to the normal vector, and that means that the point x lies on the plane. Okay, now let's see if we can't somehow come up with the equation of the plane in normal form. Let's start with the parametric form. Every point x that satisfies this equation lies on the plane. We know that much. Let's rearrange the equation, like this. Now, on one side, we once again have the vector connecting Jace's feet and the point x. Do you remember that one? It was just x minus the support vector, and now we have the same here on the left-hand side. And if you look at the whole equation, it shows us the connecting vector can be constructed from the two basis vectors. And that makes sense, of course. Obviously, the connecting vector should lie on the plane. The normal vector is always perpendicular to the connecting vector, and also to the basis vectors. Now we multiply both sides by the normal vector. Take a minute to hit pause and make sure you get all that. On the right-hand side, we have the normal vector times the basis vectors, and the scalar product here is 0, since the normal vector is obviously perpendicular to the plane that the basis vectors lie in. If you don't believe it, just try putting in some pairs of values for s and t. It always comes out as 0, so the right-hand side will be 0. So now we've made a new equation out of the old one. This one is also only satisfied when a point sits on the plane. That is the equation of the plane in normal form. And for that, you only need the normal vector and the support vector, and nothing more. Unfortunately, it's not very easy to use in calculations. So what comes next? Let's look a bit more closely at the equation. If we multiply out the left-hand side, it gives the normal vector times an arbitrary vector on the plane, minus the normal vector times the support vector. The arbitrary vector can have any set of coordinates, x, y, and z. Therefore, its scalar product with the normal vector is 1 times x plus 3 times y plus 5 times z. The second scalar product is 1 times 2 plus 3 times 8 plus 5 times 2. And don't forget that there's a minus sign in front. The calculation gives minus 36. And now we go to the result on the other side. There we have it, our final way to construct a plane, Cartesian form. This is pretty cool, not only because every math teacher seems to love it, and not because it's really slick. No, it's also really easy to use for certain calculations. For example, to check whether a point lies on the plane. How? Time for an example. We want to test, does the point 3, 4, 5 lie on the plane? Easy peasy. First of all, let's grab our Cartesian form. We put x equal to 3, y to 4, and 5 for z. That gives 3 plus 12 plus 25. Bummer. Not 36, I'm afraid. The equation doesn't agree. So, the point isn't on the plane. Just make sure you remember, if you substitute in the coordinates of the point and the result isn't the same as the value on the right-hand side, then it isn't on the plane. So what should you take away from today's video? We can describe planes in more ways than we knew before. Today we looked at 3 ways to write an equation of a plane, but they all describe the exact same plane. The parametric form shows it very clearly. The normal form, you only have to calculate the normal vector to convert it, the cross product of the basis vectors, and that's it. Then you take an arbitrary point x on the plane, calculate the vector connecting from there to the supporting point. Then you multiply that by the normal vector. The product must be 0 because x minus p always lies on the same plane. Really useful for school. Or maybe not. It's a bit like the repulsive main course you force yourself through so you can get to the dessert. Cartesian form. To get to this one, you multiply out the normal form and bring the result to the other side. This one is definitely most useful. For example, it's a real quick way to discover whether a point lies on a plane or not. That's it. Hope you have a great day. See you in the next video.